Hi, welcome back to Physics 145. Okay, we'll look at the tutorial for chapter 4, Newton's law of motion. Okay, question 1. So this is tutorial 4. Question 1. A 62 kg block, okay, is pulled along a horizontal floor by a force of 700 newtons. So this one is 700 Newton force that makes an angle of 52 with the horizontal. Now the coefficient of kinetic friction between the block and the floor is the mu value is given by 0.4. Okay, so illustrate the free body diagram for the block. Okay, so we draw that diagram. In physics, when you solve problem, diagram will help you a lot. Yeah. Okay, we have a block here. Okay, so we pull it at the force F, 700 newtons, and an angle of theta 52 degree. And then we have friction, don't forget. Okay, we have friction. So frictions will be here, okay, against the direction. The friction we use small f, which is equal to mu n, and the mu is equal to the weight of the object. Now let's assume the weight is W, and opposite direction of the weight is the normal reaction. So friction will be depending on your normal reaction. Okay, so that is the diagram. Okay, the free body diagram for the block. Those are all the forces involved. Okay, all the forces involved are already there. Force 700, weight, this is the action, and this is the reaction, normal reaction. So the friction against the direction of the motion, so is equal to mu n. Okay, see what's the next part. This number 1. Now number 2. Number 2 is compute the magnitude of the frictional force exerted in the block. Okay, now if you look at the diagram carefully, this end is not equal to W. See or not? This end is this end is equal to W. But you have to remember that our friction F, our force applied is at an angle. So now we're going to redraw another diagram, okay, with a more detailed force. Okay, with a more detailed force here. So the block, same block, okay, same block. So now our force here, this is the F at a 52 degree angle, so I put it as theta first. Now you have to know that any vector can be actually splitted into two orthogonal components. Orthogonal means they are perpendicular to each other. So now we have this vertical component, okay, and then horizontal component. Okay, horizontal component. So I will label it as Fy, and this one is the Fx. Okay, now if you look at the diagram now, okay, this force Fx is the one that moved the block to the left hand side. This is the one that is going to move it to the left if the force Fx is larger or equal to friction. Okay, now what happened to the Fy? This Fy actually pull the block up a little bit. Okay, it pull it up a little bit, so that is to reduce the reaction force, normal reaction. So we redraw the normal reaction in the same pattern like before. So we have a weight here, and this is our normal reaction. Okay, normal reaction N. This is a normal reaction when there is no force applied to the block. Okay, so this is a weight, and that is our friction now. Okay, that is our friction F. Now what we need to calculate here is the friction depends on the actual normal reaction. So we put the n prime here, okay, n prime. So why n prime? Because if you look at the diagram now, there are three forces in the vertical condition. So Fy, N, and W. Okay, so now we're going to solve the problem to find what is actually n prime. Okay, so we have this mu n prime. Okay, mu n prime. So we consider vertical components. Okay, we consider vertical component which is Fy, N, and W, and we know that the total vertical forces, okay, vertical forces is equal to 0 because the block is not moving up and down. Okay, it's still in contact with a solid surface here, okay, or the ground surface. So we assume going up, not assume, we follow coordinate system. Up is positive, down is negative. So we have Fy, okay, Fy plus n minus W is equal to 0. Is equal to 0. Oh, I think I need to put this n prime here. Okay, we need to put n prime here, sorry. Or just put it as n. Okay, never mind. This one we rub it off. We don't need the n prime. Okay, we don't need the n prime. This one just n here. Okay, this one. Sorry, my mistake. Early morning, not enough coffee. Okay, now our n now is equal to what? Is equal to W minus Fy. And what is your Fy? Your Fy is equal to F sine theta, and our W is equal to mg. So this one is minus F sine theta. So from here, we can actually put this one in to calculate the frictional force. Okay, so we know already the n value. Okay, so come to here, our m is equal to 62 kg, and then theta is equal to 52 degree, and the force F is 700 Newton. Okay, so we have enough information to calculate the n. So you can actually put into the friction formula mu n. So we have mu, okay, and then this one is mg minus F sine theta. So the mu 0.4, m 62 times 9.80 minus 700 and multiply by sine 52 degree. Okay, so let's check. We have 62 multiply 9.8, okay, and then we minus 700 multiply by sine 52. Okay, so make sure it is in degree. So we have 55 and then multiply by 0.4. Okay, 0.4, and our answer is 22.4 Newton. Okay, so that is our answer. Okay, 22.4 Newton. The answer there is 22.64, and maybe because of the G that they use. Okay, the G that they use, we are using G 9.80. Yeah. Okay. Okay, so that is our answer for question number 1. Okay, next. Number 2. Define Newton's second law of motion. Well, number 2 is easy. Newton's second law of motion states that, okay, the net force, okay, on an object is directly proportional to the rate of change of momentum of the object. Okay, if you don't want to use the extension of the on an object, you can straight away say that Newton's second law of motion states that the net force is directly proportional to the rate of change of momentum. That's it. Okay, so our formula here will be F is directly proportional to the rate of change of momentum. You can write it like this, or in a calculus form, it is like that. Okay, it means the same thing, except this one is more, we call a more delicate equation, because delta means a larger than a small d. Okay, small d, this one is more on calculus form. Yeah. Okay, so that is our what we call that, number 2. But if we want to go straight to our equations, we have F is equal to K dP dt, but by definition our K is equal to 1 because we want our F to be in a unit of Newton, the mass in kilogram, and then our acceleration in a unit of meter per second per second. So we assume here, so if the unit of force F is in Newton and the unit of mass and acceleration, okay, A are respectively kilogram and meter per second, then K is required to be equal to 1. Okay, so normally we don't need you to know about all this deep theory. So our F is equal to the rate of change of momentum, but we know that our momentum is equal to mv. Okay, so by using the basic knowledge that you have about differentiation, we can split this one into 2 terms, which is number 1 dv dt plus v dm dt. So this one is called our rocket equation. Okay, why? Because of the dm dt. Okay, dm dt, but that is just a name for it. But okay, we know that the rate of change of velocity is acceleration, right? So equation can be simplified to something that looks like that. So that means net force actually come from two ways that you can actually have the force. One is if the object is accelerated, it need a force. And then if you have, for example, you throw something away from vehicles at a constant velocity, you also produce force. So, but that one is in a system that is very complicated, like rockets. Okay, when you throw, when you burn gas, you dump the gas out from the rocket, you have dm dt at a high velocity, you produce a force, and finally you have an acceleration. Okay, but if in normal situation where the changes of mass is very small, okay, so like that, if our dm dt is very small, then our equation F is equal to ma. That one is our main equation used in this chapter. Okay, so there is our F equal to ma. So that one is a special case here. So this one is a general case. Okay, a general case. Okay, I write here, and this one is special, one is general. Yeah? So this one is our general case, and this one is a special case. Special case means when the rate of change of mass is very small. This one is you calculate it. Okay, so that is our answer for question 2. So it doesn't seem to be that simple actually. Okay, so the question looks very simple. All right, so we go to the next one. This is our page 1. Okay, go to page 2, question 3 now. Question 3. Now we have 2 objects, A and B. Figure 2 shows 2 blocks A and B of mass 4 kg and 6 kg respectively are connected by a string on a smooth horizontal surface, no friction. So if the tension in the string is 7.9 Newton, this one here, okay. So if the tension in the string is 7.9 Newton, okay, compute the acceleration of A and B, okay, A and B. So because the force is applied on A, and then the force F here partially will be transferred to B depending on the ratio of the mass A and B. If the B is more massive than A, in this case, yes, 6 larger than 4, So you need a larger force applied to the B, but the ratio will be automatically, naturally distributed among each other. Okay, so you cannot have both apply the same force. If both apply the same force, definitely your B will be actually what we call that, accelerated less than A, and finally they are getting further and further apart. Okay, so that one we assume that they can distributed naturally by itself. And then another assumption is we assume that the string is inelastic. You cannot stretch the string like rubber band. Okay, so we solve this problem now. Okay, this is first we need to have a free body diagram. Okay, so we have two boxes. Okay, I would like to use this one, it's easier. Okay, we have a small box here. And then we, oh, never mind, we draw that one later. And then we have a larger one here. Okay, so this is our box. And this one is our floor. So I apply a force F horizontally according to the diagram. Okay, and then a string is attached between A and B. So this one is 4 kg, this one is 6 kg. Okay, we have to assume the string or the rod is inelastic. Okay, inelastic. Okay, and we know that already the floor is smooth. So we need to label all the forces involved. F is already there. Okay, F is already there, and we know that there is an action, there is a reaction. Okay, unknown T, and then that is how we look at the system A now, assuming the B is not there. So we know that when you pull B, you pull the A will pull the B, and this one is a reaction. Okay, so what happened next is, now you look at what happened between A and B. There's a piece of string. If there is a piece of string only, you cannot have just one force F, a T only. It must come as a pair. Now we draw another one. Okay, we draw another one. So now we know that there is an opposite tension. Okay, this is the one that pulled the B. Okay, and now what happened to this T? This T here is the one that pull A backward by B. Okay, now another one is the B, okay, does not A and B does not experience any friction, so that friction is equal to 0. All right, so now we can calculate, okay, the acceleration. Now since we already assume the string is inelastic, so both will experience the same acceleration A in the direction of the force F. Okay, so we already know one thing given to you. Okay, T is equal to 7.9 Newton. So if you already know T is 7.9 Newtons, you can actually calculate the acceleration for B, because B only experienced one force, okay, T, and according to Newton's second law in a special case, okay, so we use this F equal to ma. F is the net force. So for B, okay, from this one is for block B, so we have only one force, T is equal to ma, and our A is equal to the tension divided by the mass. So the tension is already given 7.9 Newton, and then divide by the mass of 6 kg. Okay, so we have this 7.9 divided by 6, so we get 1.32 meter per second per second. So that is the acceleration for B. Okay, but the same acceleration apply to A as well. Okay, next, the force applied to the boxes. Okay, what is the meaning of that? That means find F. Okay, find F. So from number 2, we consider, okay, consider block A. Okay, consider block A only. So now we look at the block A. Block A experienced two forces. One is the F, another one is the tension. and which is a mass of 4 kg and experience acceleration A. So according to F equal to ma, okay, the force, this is a net force, yeah, net force, sorry, forgot to put this one. So the net force on block A cause it to accelerate, okay, to that direction. So the net force here is F plus negative T. So we have F minus T is equal to ma. The m here is 4 kg. A is already calculated. Unless part 1 is wrong, your B will also be wrong, okay. So F is what we need, and T plus ma. So this one is 7.9 plus 4 times 1.32. So let's have a look. So with this one, we multiply by 4 and then plus 7.9. So we have 13.2 Newton. Okay, so this force will be redistributed automatically so that both A and B under the string which is unstretched condition, so that your B also experience the same acceleration. Okay, so that's number 3. Next, number 4. Okay, question 4. State Newton's third law of motion. Okay. Newton's third law of motion states that every action will have an equal but opposite reaction. Okay, that's it. That is Newton's third law. Okay, Newton's third law. Yeah. So for example, you have an object. Okay, you have an object on the floor. Okay, you have an object on the floor. This object here will experience a force, and this force is a downward force which is act by gravity. So we call this one the weight. But if there's nothing support the block, then the block will actually move directly downwards toward the center of the earth. Okay, so since the block is not moving, there must be some other forces acting on it. So in this case, it's a normal reaction. Okay, N. Now, if we look at these two forces as a vector, then we know that the direction of the N is the opposite of W. W weight is downward, N is upward, so they are opposite. Okay, so opposite of W in the form of vector. Yeah, but if we consider their magnitude, they will have the same magnitude. Okay, magnitude of M is equal to the magnitude of W. That is the third law. Okay, that is the third law. Okay, done. Third law done. Now come to the next one. Give 2 examples of Newton's third law of motion. Oh, we already give example. Okay, number 1. Okay, next one. So we consider this one as number 5. Yeah, number 5, example 1. We go to another example. Okay, so another example is what? This one is vertical. So if you want to give example on other direction, also can, no problem, like horizontal condition. For example, you lean against a wall. Okay, not you lah, ladder. Okay, a ladder against a wall. This is the wall. Okay, assume smooth wall, but the floor is rough. So I put a ladder against a wall. This is what happened. Yeah? So we label all the forces involved. Of course, the one that I use black color is not our concern that much. Okay, this is a weight. Okay, this is a weight. Now, anything in contact, any solid surface in contact will have reaction. Okay, will have reaction. So for example, the first one is the floor. Okay, the first one is the floor. and then the second one is a wall. Okay, this one. So now, why they have reaction? Because the ladder is imparting a force on the wall. So you have force going into, not going, imparted into the wall. So we call this one Fx. And then there is another force, okay, coming downwards against the floor from the ladder also. This is your Fy. So this is an action and this is a reaction. So this one is the normal reaction horizontally, and this is a reaction from your Fy, and this one is the Ny. So you see, we have two components involved. One is a horizontal, one is component, one is a vertical. All right. Of course, since the floor is rough, so we have another force involved, which is the friction in this direction. Because what happened is, if the floor is also smooth, the whole ladder, okay, is going to slide down like that, right? Okay, I think you experienced it before. If you climb a ladder where the floor is slippery and finally end up not climbing, but you are slipping on the floor. Okay, so that is what we have for that two example in number 5. All right. Okay, next one. Number 6. Okay, this is number 6 here. So our 6. Figure 3 shows object A and B with masses of MA equal to 3.5 and B is 7. So the object is going to, B is going to fall down, respectively connected by a light rod that runs on a frictionless pulley. And we also assume the string or the rod is not stretchable, is inelastic. When B is released, the two objects move and A undergoes a 2 newtons frictional force. Well, maybe you don't use the word undergoes, or we say it's experience. Okay, compute the acceleration of the system and the tension of the rod. Okay, B is falling down, but not under free fall, because there's something actually that stop it from doing that. Okay, so we have this table and then the floor here. Now we have a pulley. So block A is here. And our B is here. Okay, there's a B. Right, and then this is a string. Alright, now we label the force. So A, B, and this one is 3.5 kg, and this one is 7.0 kg. Now B, okay, we look at B first. B is act upon by gravity, so we have a mg, okay, and then action will produce a reaction tension. Okay, we don't know this value, and this tension will be distributed along the line, along the rope, and started to pull A. Okay, so as long as a pulley is smooth and the rope is inelastic, we have this tension which is equal to this one. If your pulley is rough, have friction, the tension here will be less than the tension here. So you don't worry about that, because all the pulley made by God are what we call it, smooth. Okay, and then another thing happened to A is it experienced a friction, okay, F, which is equal to 2 Newton. Okay, so by assuming that the whole system does not the pulley is not rough or smooth, so A experienced acceleration A, and B experienced acceleration A also, except the direction are different. Okay, so we have to form equations here. You need 2 equations because you have 2 unknown. One is A, another one is T. Okay, so we look at A first. Okay, for A, we use net force is equal to MA. Okay, so now we have to look at things carefully here. We use vector here to solve. So our direction going to the right is positive X, and then going up is positive Y. So you stay cautious about this direction. You won't make any mistake in the sign positive and negative. Okay, so now we have A. Now for block A, this is horizontal forces. T pointing to the right, positive. F, small f pointing to the left, negative. Your acceleration to the right is considered positive. Yeah, follow the direction of the big T. So we have T minus F is equal to MA. But this mass is belong to A, so MA. A. So we have T minus 2 is equal to 3.5A. Okay, we just leave the equation like that. So we call this one equation 1. And then for B, same thing here. Now we consider total force in the direction, vertical direction. So T is positive minus, okay, the weight of the object B. So we have MBG and mass equal to MA, right? But your A, if you look at the direction, is downward. Okay, so we follow everything vector. So now put in the value T minus this one is 7G, and now this one is equal to negative 7A. Alright, so we have number 2 now. Now if you want to solve, okay, you want to solve for value of A. Number 1, acceleration, equation 1 and 2. You want to find A, you have to cancel T. So it's very easy here. We use 1 minus 2. So when T, this 1 minus T, T gone. And now 2 minus 7G. Okay? Negative 2 minus the negative 7G. And this one is 3.5A minus negative 7A. So now here we're going to get 10.5A because you sum up, right? 10.5A. And this one is going to become 7G minus 2. Alright, so we can calculate our A here. Okay, so let's have a look. So 7 times 9.8, okay, minus 2, you got 66, and then divide by 10.5. So we got 6.34. 6.34 meter per second per second. Okay, that's the first one. Alright, next, the tension in the rope. Well, you can actually calculate from any equation 1 and 2. Say from number 2, let's say. I'll say from number 1. Okay, so from number 1, our T minus 2 equal to 3.5 times 6.34. So we can get our tension here, 6.34 multiplied by 3.5. Okay, and then plus 2, so we have 24.2 Newton. Okay, so that is how we solve this type of question. Okay, so that's our page number 2 and question number 6. Okay, next, question number 7 now. Okay, question number 7. Okay, question 7. Did you realize that this one is the same as question number 1? Okay, I'll just say it like this. Refer to question number 1. Okay, refer to question number 1 is the same unless you feel that left-handed people are smarter than the right-handed, then you are wrong. It's the same question here. Okay, alright, the only thing different is this is 750 and this is 64 kg, and question number 1 here 62 kg and this one is 700. Alright, so the rest are the same, only the diagram change sided. Okay, instead of left, now it go to the right. Okay, so question 7 just like that. Now we go to number 8. Page 3. Okay, number 8, we have two objects in contact. Okay, two objects in contact. Okay, we draw the object in contact first. Flow. And then we have object in contact, larger one behind. Okay, we have this one. And then a smaller one in contact like that. Okay, so that is A. and this one is B, and they are 13 and 0.0 kilogram, and this one is 5.0 kilogram, and a force is applied to it, F. Okay, let's look at the question. A block of mass 13 kg rests on a smooth and horizontal floor next to a box of mass 5 kg, as shown in a diagram. The 13 kg block is then pushed with a horizontal force of 40 Newton. Okay, this one is 40 Newton. Draw a free body diagram for each block in figure 5. Okay, so now we draw the force involved. F is pushed against A. Okay, and then what happened is A have to push B. So we draw this one. The force from A to B is in this direction, and we call this one FAB. Okay, FAB. But anything in contact, every action will have an opposite and equal but opposite reaction. So when A push B, B will push back at A. Okay, B will push back at A. So this force here I will call BA. Okay. Now we know one thing about that two forces. Okay, these two forces have the same same magnitude. Okay, the force AB have the same magnitude as the force BA. The only thing different is they are in an opposite direction. Okay, they are in an opposite direction. So that is our diagram, free body diagram for number 1. Next, we go to number 2. Of course, we have weight here, but since the friction is not existing, okay, friction is not existing, so we can assume that we don't have to draw the weight because the normal reaction will not be in any use for us. Okay, next one is number 2. Compute the acceleration of the blocks. Okay, so since they are in contact, so we assume that they have a common acceleration A. Okay, common acceleration A. So the first thing we need is we need to solve the problem of the FAB and the FBA. So we consider forces acting on individual block. First, we look at A. Okay, this is A. Okay, this is A. Okay, block A, you apply a force F. Pushing is the same as pulling when we draw in a diagram, and then it experiences a force from B. Okay, and this force here is FAB. Okay, sorry, BA, mistake, BA. This is BA. Now it experiences also acceleration A. Okay, so we form equation. Okay, so we know that total force on A is equal to MA. So our force, assume that right again is positive X, right? So we have F minus FBA is equal to MAA. So our value is 40 minus FBA. This is unknown, and this one is 13 kilogram. So I have equation number 1. Okay, equation number 1. Okay, next we look at diagram for B. Okay, we look at B. So B is this one. Yeah? B only experience one force, which is FAB. Okay, FAB. So this is B, and also experience the same acceleration A. So we have total force, net force on B is equal to MA, and there's only one force, FAB is equal to 5A. Okay, so this is our equation number 2. So now we solve that two equation, but we already know that magnitude of FAB is the same as magnitude of FBA, right? So we can actually replace, put number 2 into number 1. Okay, so but we write something here. Since magnitude of FAB is the same as the magnitude of FBA, so we can actually put number 2 into number 1 here. This one put into here. So now we have 40 minus 5A is equal to 13A. So now we have 18A is equal to 40. So we can calculate our A here. Okay. So we have 40 divided by 18 and we get 2.22. Okay. 2.22 meter per second per second. Alright. So that is our answer for the second one. Okay. 2.22. Alright. Next. Compute the contact force between the blocks. Okay. Since you already have A from equation number 2, okay, from equation number 2, our FAB is equal to 5A, which is equal to 5 times 2.22. Okay, so we times 5, this is what we get, 11.1. Okay, 11.1 newtons. Okay, 11.1 newtons. So what we have here is we have two different force FAB, another one is FBA. So the magnitude of FBA is the same as the magnitude of FAB. So the answer is also 11.1 Newton. Okay, 11.1 newtons. Alright, but unless you want to draw, you want to write down your answer in the form of vector, then we have something different here. FAB pointing to the right hand side. So your FAB is equal to positive 11.1 I Newton, and your FBA is equal to negative 11.1 I Newton. So you see they're opposite in direction because of positive I and negative I, but the magnitude are the same. Okay, but since question didn't ask for the direction, you can leave your answer just like that. Okay, alright, so there is question number 8 done. Next one, question number 9. Okay, question number 9. Question number 9 is an inclined plane. Okay, inclined plane. At an angle of 42. A block here. Okay, a block is here. So I have a block. Okay, use a smaller one. Another one is here. Okay, another one will be here. Okay, so the string is going to pass through a pulley. And connected to B. Okay, so that is a pulley, smooth pulley. Okay, so this is A, this is B. Okay, let's read the question first. Figure 6 shows two objects A and B of 7 kg. Okay, this one is 7 kg and a B is 8 kg. Okay, and connected by a light string that passes over a frictionless pulley. Object B lies on a smooth surface, inclined plane of 42, no friction. Sketch the free body diagram of object A and B. Determine the acceleration of the system. Okay, now, and also the last one, determine the tension of the string. Now, guess in what direction is the object going to move? I will guess that A is coming down, B is going up. Okay, that's what we get. Guess. If the answer is wrong, we're going to get a negative answer. Okay, so sometimes first you have to have a guesswork correctly. Okay, first draw all the forces involved. Okay, number 1, we look at A. Weight. This is MAG. And then tension in the string T. And then since the string is inelastic and the pulley is frictionless, so we have another tension applied to B, same value T. Okay, and then one more is B have a weight component that is pointing downwards. Okay, like this. This one is mg sine theta. That theta is here. Okay, so mg sine theta, and this m refer to 8 kg, this m refer to 7 kg. Yeah. Okay, so now we need to form equation because that is for number 2. You need to form equation because there are two things you don't know, T and acceleration A. So we assume that A coming down with acceleration like that, and B accelerate upwards. Alright. Okay, we'll look at the easy one first. Yeah? Okay, number 1 done. Number 2, block A. Okay, we look at block A. all our vertical forces. Remember, up is positive y, down is negative y. Yeah? So total force acting on A is MA. So the total force involved is T minus MAG is equal to MAA. Alright, so our T unknown, but the mass you know is 7. So 7G is equal to 7A. And this is our equation 1. And now look at block B. Okay, your neck had to be twisted by 42 degrees. Look at B. So now we assume, if we look at the inclined plane, we can assume things like this will happen. Yeah, okay, things like this will happen. Okay, X here positive, this one is Y. Okay, positive, but since there's no vertical motion like that, so we assume only along the inclined plane. So our total force again is still equal to MA, except now it apply to B now. Okay, up is according to our definition, X is negative, so we have negative T, and then plus this one, because this one is according to the direction. Okay, so plus MBG sine theta, and it's equal to MBA. Okay, now put in the value, we have negative T plus, what is this one? This one is 8, right? So 8G sine 42 is equal to 8A. So now you have equation number 2. Okay, equation number 2. Now the next, this number 2 is to determine the acceleration of the system. Find A. Easy. Sum up 1 and 2. Okay, 1 plus 2, your T gone. So now you only have these two. So you have at G sine 42 minus 7G is equal to, you sum up become 15A. Okay, so we can calculate the A value here. Okay, we have 8 times 9.8 times sine 42. Okay, we have this minus 7 times 9.8. Okay, we have negative 16. Correct? So that means A is supposed to be going up. Correct or not? Correct or not? Okay. Oh, no, not yet. Okay, never mind. So our negative is just the direction. And then divide by 15, divide by 15. So we have negative 1.08 meter per second per second. Okay, is correct. This one. So now what happened here is, our A is negative because it go down in this direction, right? Because we know that up is positive y, down is negative. So A is moving downward, accelerate downwards is correct. Okay. Because we use vector, I've forgotten. The answer gives you 1.08 positive. It does not tell you in what direction. So A is moving upwards now. For B, moving upwards. Okay, B moving upwards here. Again, moving up is negative x, right? See or not? Up is negative x, so this one apply correctly. Okay, negative 1.08. Okay, number 3. We have determined the tension in the string, so we can use any one of the equation. T, we use number 1 here. T minus 7G is equal to 7A. So the T is 7G plus 7A. Okay, so now we already have the A here, but you have to put in whatever you calculated. Yeah, you don't put in the magnitude only. So now we have 7A, which is this one. Okay, so times 7, and then we sum up with 7 times 9.8. Okay, so now we have 61.1. Okay, 61.1 Newton. All right. So don't drop out the negative sign. Yeah? You drop out the negative sign, you're going to get the wrong answer already. Okay. So everything must go according to vector, so that you got no problem with that. Alright, that is number 3. Now we go to page number 4, which is question number 10 now. Page 4. Question 10. Okay, question 10. A van of 1,500 kg is speeding at 26. Compute the resultant force required to stop the van in 75 meter on a level rod. Alright, this is kinematic plus Newton's second law. So we list down what we have here. A mass of the van, 1500 kg, is speeding with an initial speed of 26, velocity, meter per second. You want to stop it, so the V must be 0, and the displacement is 75 meter. Right? To calculate the resultant force, the only force that can stop the vehicles is the braking force, and that braking force is the one that creates the friction. Okay, so we expect the friction to have a negative sign. So first, we know that we are going to use Newton's second law special case equation, F equal to ma. So you need A. Okay, you need the A value to calculate the force. So how to get A? By looking at UVS, we know that there's one equation we can use conveniently, is this one. Plus 2AS, this is 0, 26 square, plus 2A and 75. So A should be negative in this case. So we have 26 square, and then divide by 2 times 75 here. Okay, so we have negative 4.51 meter per second per second. Okay, so there is a deceleration experienced by the van. So from Newton's second law, the total force experienced is equal to ma, and the force we know is a friction, which is 1005 multiplied by 4.51 negative. So we use this one, multiply 1500. So I have 6,000, negative 6,760 Newton. We round up the answer because this is too much of the accuracy already. Okay. Alright, so that is question number 10. Now, question 11. How many questions you have? Oh, not many left. Okay, question number 11 now. It's an inclined plane again. Figure 7 shows a 12 kg box placed on a 30-degree smooth inclined plane. Compute the force P to cause a box to accelerate down the plane at 8 meter per second per second. Okay, you need to apply a force. Compute the force F. Okay, first we draw the forces acting on the box first. Okay, so I have a box here. Okay, so if we look at the component that actually pull the box down, we have this. This is a weight, mg, right? Now the force weight, okay, or the weight can actually be split into two components. Okay, two components. One, okay, is parallel to the surface. This one here. Okay, this is the one that is parallel to the surface. So if the weight is W, so this force here is actually equal to W parallel. And there is another component you can split, is this one. And this one, okay, and this one here is W perpendicular. Okay, but since the surface is smooth, so our W perpendicular is not important to us because it contributes to the friction. So this one here, okay, this one is theta also. So we know that this force here will be mg cosine theta. And this one here, our W parallel, is equal to mg sine theta. Okay, remember your geometry here. So go back and study your geometry. Alright, now the question asks about what force is needed if you need to accelerate the object down with an acceleration of 8 meter per second per second. So need a force. Okay, you need to apply a force unknown F so that the object, okay, the block here, accelerate downward equal to 8 meter per second per second. That's the information given to you. Okay, so let's start. Okay, So now we have to take consideration, okay, the direction. So you see, all the vectors are pointing downward, right? Remember the previous question? The previous question, I choose downward is positive, right? So now you can actually choose downward to be positive also if you want, okay? So you can choose this one downward to be positive for our convenience, okay? For our convenience, and this one is positive because coordinate system, even though we know that we don't supposed to change the direction of positive x and y, but we can do that for our convenience. So now since we choose downward to be positive, so now we have P positive, W parallel positive, and then A also positive, so it's much easier for us, okay? So now we consider downward motion, okay? And the total downward motion, which is parallel to the surface, must equal to MA. We already know this one. Now the box here has a mass of 12 kg, okay, 12 kg. So all the forces involved is P plus W parallel, don't forget that, and is equal to MA, okay? And the P is what we need to calculate, so it's equal to MA minus W parallel. So our M is this one, 12. So 12 times 8 minus this one, mg sine theta, sorry, I forgot to write now, minus mg sine theta. So this one already here. So now this is 12 times g8, and then sine theta is 30 degree. Sine 30 is half, right? Okay. So we have 12 times 8, and then minus this one, 12 times 8 times sine 30 degree. Alright, so we have 48, okay? We have 48, okay? 48 Newton, okay? 48 Newton. Now, you know why the answer is 37.14, okay? 37.14, because the question didn't clarify, okay? Clearly, are we talking about extra forces or the combination of the forces, right? Now, if we look at the total force, let's say, okay, the total force, okay, if we look at the total force, let's assume we call this force P prime. What's the total force? Your total force P prime is equal to P plus W parallel, right? So that means it is only equal to MA. Okay, it's equal to MA. You don't even need to go to that such a difficult way to solve the problem. Okay, let's check first before I make any wrong conclusion. 48. Okay, so no friction here. So we have to minus that component. So we already know the P is 48. Now, okay, oh sorry, this is the P. Something is wrong with the answer here. Something is wrong in the answer here. Let's check mine. Downwards, mg sine theta, sorry, W parallel mg sine theta. This is 30 degree, right? Okay, the mass is 12. That's it. 8 meter per second, yeah. So we have this total force downward is equal to P plus W parallel equal to MA. So I have MA minus W parallel, which is mg sine theta. So 12 times 8 minus 12. Oh, sorry, my mistake here. This is not 8. 9.8. Sorry, my mistake. Okay. 9.8. Okay, see what happened now? 12 times 8, okay, minus 12 times 9.8 times sine 30 degree. Should be correct now. 37.2. Okay, blame the wrong person. Newton. Okay. Now, let's say the question asks you the total force. Okay, if the question asks you the total force, then you need to sum up these two. Okay, you need to sum them up, right? So this one will be now 37. Okay, because you sum up, you see, P plus W parallel. P plus W parallel is equal to MA from here. So what is your answer? This one will be equal to 8 times, 12 times x. Okay, 12 times x, we go according to formula. 12 times 8, this one will be 96 Newton. Okay, 96 Newton. Alright, so it depends on what the question is asking. Yeah? In this case, is the extra forces needed, so we need only 37.2. Because even if you don't pull it down, the block will still slide down. Okay, it will slide down because of the mg sine theta. But because you apply extra force, it's going to slide down faster. Okay, slide down at a higher acceleration value. Okay, so that is question 11. Okay, next. Question 12. Okay, question 12. Alright, we have an inclined plane again. Figure 8 above shows a block of mass 10 kg held by a string on a frictionless inclined plane at angle 50 with a horizontal plane. List two forces acting on the block. Sketch a free body diagram for the block. Okay, refer to this block. So this thing is 10 kg. Yeah? So we draw the diagram again. So we have a big block here. Pulling, okay, so I have box, okay, a string. Normally when we attach a string, we have to make sure that the string is parallel with the surface here. So this is theta, where theta is equal to 50 degree, and the blocks here have a mass of 10 kg. Okay, list two forces acting on a block. Well, number one is clearly is a tension. Okay, so we have a tension in the string. Okay, we call it T. That's number one. Number two, remember that component, this W parallel. Okay, the component. Okay, component of weight of the block, okay, parallel with the inclined surface, with the inclined plane. Alright, and we call this one W parallel. Alright, okay, so that is the first one. B, sketch a free body diagram of the block. Okay, free body diagram. First, we have tension in the string. There is a T, and then we have the W parallel. Okay, and our W parallel is mg sine theta. Okay, mg sine theta. So that is our B done already. Now compute the tension in the string. Okay, C. Tension in the string, so the object stationary. Okay, it stay there, held, because it says held by a string on a frictional surface. So the T is the one that support the W parallel. So we consider, okay, forces parallel to the surface or along the surface. Okay, parallel to the surface. So we have total force must equal to 0. Parallel with the surface. Yeah. So now we choose either direction to be positive. You can choose like this now. Okay, this one positive Y. So now we choose, okay, doesn't matter lah. Downward positive also can. Okay, positive X. Okay, so we have positive W parallel minus T is equal to 0. So finally the T is equal to W parallel. Still the same thing, right? If you choose this one upward to be positive, you get this positive minus W parallel equal to 0. So you still end up the same thing. Okay, so we can calculate the T by using W parallel, which is equal to mg sine theta. So the mass is 10, G is 9.8, and then the angle is 50. Okay, so let's check. Times 9.8 times sine 50. Okay, answer is 75.07.1. 75.1 Newton. Done. Okay. D, calculate the reaction force on a block. Okay, what's the reaction force? Now we need that reaction force. We know that force that is perpendicular to the surface here, we have another one, is this one. Remember, this is W perpendicular here, okay, which is equal to mg cosine theta. But this is the action on the surface of the incline. So there will be a reaction from the surface, which I will call N. Okay, so your N is the reaction from W perpendicular. So that means it has the same magnitude, only in the opposite direction. Yeah. So we calculate the reaction. Okay, the reaction force N is equal to the magnitude of W parallel. So it's equal to mg cosine theta 10 times 9.80 and cosine 50. Alright, so we have 10 times 9.8 times cosine 50, right? Answer 63.0. Okay, 63.0 Newton. Okay, alright, so that is our question number 12. Next, page 5. Question 13. This is page 5. Question 13. Looks quite the same. Describe a situation where Newton's third law applies. Describe a situation where Newton's third law applies. Okay. Well, it's very easy. Let's look at someone sitting on a chair. Okay. And the chair is on the floor, and the floor is in a building, and the building is on the surface of the earth. So let's look at a normal chair. Okay. So this is a very normal chair, which I have at home also, like that. It doesn't look quite normal here. Okay. This is me. Okay. And this is my thigh. And this is my leg. Normally I like sitting hanging. Okay, my leg above from the chair. And this is my hair. This is my head. Okay, assuming. Last time I don't used to have a big tummy, but now I think recently because of MCO, no exercise, okay, don't go out that much, so increase by a few kilograms. Okay. Now I'm only 70 kilograms, you know, believe it or not. Okay, next. Question asks about where are we going to apply this one. Okay, look at the chair, look at the person here. So the weight, okay, the weight is downwards. W equal to mg. That is an action. Okay, that is an action. Now, where does the reaction? The reaction is actually distributed along the contact surface here. Along the contact surface here. And of course, if I touch the back of the seat, the friction will also give me some support. But I assume that I don't touch the seat properly, with my backside not touching the, my back not touching the chair support. Okay, so you see there is a gap here. So now I assume it all concentrate on the butt here. Okay, so that is the normal reaction. Okay, normal reaction, we normally assume a dimensionless object lah. Okay, so we write down the statement here. Now what is the statement there? Describe a situation where Newton's third law apply. Okay, Newton's third law said that stated that every action will have a equal but opposite reaction, right? Yeah. So when a person, okay, sits on a chair, okay, its weight is the action of gravity. Okay, so now according to Newton's third law of motion, okay, there will be an equal but opposite reaction. okay, applied to the person. Okay, in this case it is the normal reactions n. Okay, so clear, right? It's a normal reaction n that actually balance all the forces. All right, so that is question number 13. Easy peasy. Next, question 14. Okay, question 14. Question 14. A force F, a force P is exerted on a block of weight 15 Newton as shown in figure 9. The block is accelerated by 9.9. Oh, okay, it's much actually accelerated larger than the free fall. Okay, on a smooth horizontal surface, sketch a free body diagram of the system. Okay, this question is actually quite the same as one of the previous question we have done. Okay, we have a block here. Now you apply a force at an angle 25. Okay, at an angle 25, 15, sorry, the weight is 15 Newton. Okay, the weight is 15 Newton. Yeah. Okay, the force is F at the angle theta. So we have a weight here. Okay, the weight is W is equal to mg, and it is equal to 15 Newton. Okay, this one is 15 Newton. All right. Now, one more thing is you accelerate the box, okay, in the direction of the component of force with A equal to 9.9 meter per second per second. It's smooth, so no friction involved. Okay. Oh, sorry. This is P, not F. Okay, P. Now, we have to look at the force P first. We know that it can be split into two components. Okay. One is vertical, this one. Another one is horizontal. Okay, horizontal. So this is a PY, and this is the PX. Okay, there is a PX. Now, this PY is going to contribute to the normal reaction of this block. But since the surface is smooth, so there is no friction. So we don't have to consider, we don't have to pay attention to our PY and also N. We just need to look at PX. Okay, so what is PX? We have to calculate PX first, because PX is the one that is going to, what we call it, accelerate the object to the left hand side. Okay, so total force in the direction of the X is equal to MA. So now we assume to the left is positive. Yeah? So we assume something like this. This is positive X. Okay, so positive X direction to the left. So now we have PX is equal to MA. But we don't have M, right? Okay, our M is equal to W over G. Alright, so we can calculate like that. So PX, okay. Now our W is 15, and then A is 9.9, and then divide by the G, 9.8. So we got our PX. Okay, we calculate the PX first here. 15 times 9.9, and then divide by 9.8. So we have 15.2 Newton. But that is PX. Okay, we want P. But we know PX is equal to P cosine theta. Okay, PX is equal to cosine theta, P cosine theta. So our P is equal to 15.2 divided by cosine theta, and your theta is equal to 25 degrees. Okay, so from here we can get our P. So use this one, divide by 15.2 divided by cosine 25. Okay, so we got 16.8. Okay, 16.8, yeah, Newton. Okay, next This one is number A. This is B. Now we calculate for number C. Compute the normal force acting on the blocks. Oh, we still need the normal force, yeah? Okay, normal force is this one. Okay, so now C, we assume now upward is positive Y. So now our C will be total force vertically is equal to 0 because it's not moving up and down, so not equal to MA here. So you need to know when is equal MA, when is equal to 0. So assume the block is not moving up and down, it just slide along the horizontal surface. So total forces will be PY plus N is equal to W. Why? Because minus W equal to 0. So it's equal to W. So you need to find N. N is equal to W minus PY, and W is equal to 15, but we write W first because you need to split this one. This one become P sine theta. Okay, so this one is 15 minus your P is 16.8 and sine 25. Okay, so let's check. 15 minus 16 sine 25. Okay, answer is 8 point is it correct? 25. Oh, sorry, 16.8. Okay, 15 minus 16.8 sine 25. Okay, we have 7.90 Newton. Okay, 7.90 Newton. Okay. Okay, so that is question number 14 done. Oh, two more. Okay, next question 15. Question 15 here. Figure above. Oh, where's the figure above? Oh, here. Okay, incline plane. So we draw that one first. Incline plane. There's an object on the surface here. Okay. Figure above shows a 120 kg box. Oh, heavy. M equal to 120 kg. Sliding down on a rough incline. Now friction become important. And an angle of 35. Theta is 35 degree. Given the coefficient of friction, okay, the surface here have a kinetic friction equal to 0.25. Okay, sketch a free body diagram of the system. Free body diagram. Okay, we draw all the forces involved. We know that first we have a weight here. Downward force weight equal to mg. Okay, and this force can be split into two components. Don't know how many times to repeat this thing here, but for your own good, the more you repeat, the more easier to remember. Okay, this is a component. I call this one W parallel, and one more is this one here. This one is W perpendicular. Okay, this is the one that contribute to the friction. Yeah. Okay, now the box is sliding down, nothing pull it, but we have one more thing here is a friction. See, friction, because it slide down, so we have friction F, which is equal to mu n. And where's the n come from? The n come from here, and this n is equal to W perpendicular. Okay, so those are the forces involved: W parallel, W perpendicular, friction, and normal reaction. Yeah. Okay, compute the frictional force. Sorry, A. B. Friction is equal to mu n, but since we are talking about sliding, it already started to move, so it's a mu k. So mu k is given 0.25, and then the normal reaction is equal to this component, and our n is equal to perpendicular, so I have mu k mg cosine theta. Alright, 0.25, 120 kg times 9.80, and then cosine 35 degree. Okay, let's check the answer. 0.25 times 120 times 9.8 times cosine 35. Okay, so answer is 241. Okay, 241. Yeah. we give our answer normally to 3 significant figures. Yeah. Okay, next, see, compute the acceleration of the system. Okay, it slide down with acceleration A. Now we have to consider all the forces parallel to the surface. Consider all forces along the surface. So now we assume that this direction is positive x. Okay, positive x. So now our force parallel to the surface is equal to ma. So what are the forces parallel to the surface? There's only two, W parallel and F. Okay, so this one downward positive, right? So W parallel minus F is equal to ma. So I need to calculate acceleration. So we put our A to this side here. ma is equal to W parallel is mg sine theta and minus the friction. So friction already calculated. So we have put in the value. This is what? This is 120 times 9.8 and then sine 35 minus 241. So don't forget to divide by m later on. Okay, 120 times 9.8 times sine 35. Okay, minus 241 and then divide by the mass of 120. So answer is 3.61 meter per second per second. Okay, so that is question number 15. Last one, 16. Okay, 16. See what happened. Oi, I think they have some mistake here. This one should be Dr. Ahmad Lutfi. It's more correct. So Dr. Ahmad Lutfi sees a toy trolley at rest on a smooth horizontal table. Identify which Newton's law would help Ahmad Lutfi or Dr. Ahmad Lutfi to describe the motion of the trolley. State the law. Okay, stationary at rest. Okay, at rest. So there are two, right? There are two laws. Okay, identify which Newton's law would help Ahmad Lutfi to describe the motion of the trolley. Okay, we just put the trolley on the floor. Okay, on the floor. So the trolley, okay, the trolley is not moving. So we see that it's logic. Okay, it is logic. So the trolley is, okay, not moving. If it is moving, something is very wrong without anyone pushing. Okay, this is our trolley. Okay, we label all the forces first. Okay, number one, okay, number one, it have weight. And then the next one is normal reaction from the wheels. So we call that the total N1, N2, and after that we total it up. So we assume N is equal to N1 plus N2. Okay, so we consider this thing to have two dimensions. Okay, so first we consider, okay, according to Newton's what we call that, we look at second law first. Okay, according to Newton's second law. Okay, according to Newton's second law of motion, of course, the action of gravity give the weight of trolley downward, W. Okay, and this action, okay, this action will create, okay, an equal but opposite reaction. Okay, N. Okay, N. Your N is a total reaction from all the four wheels. Supposed to be N1, N2, N3, N4 because trolley have four wheels, right? So we just simplify them as N. Okay, N. So this is what happened here. Okay, opposite but equal. So that means the trolley is not moving up and down. Okay, so according now, okay, then according to Newton's first law of motion, okay, since the total vertical force is equal to 0 and the total horizontal forces is equal to 0 because there's no one pushing it, because it's say at rest, alright, nothing push it. Okay, so since these both forces total, the net force vertically and horizontally are 0, the trolley, okay, will stay stationary. Okay, stationary. Okay, so at rest. So that is how you explain question number 16 according to Dr. Ahmad Lutfi. Alright, okay, so that is page 6, end of the tutorial number 4, chapter 4. Yeah, okay, see you next time.